Shakespeare said that the eye is the window to the soul, but based on current research, the eye could also be a window to our multiple sclerosis. Well, hello and welcome to another episode of You and Me and Multiple Sclerosis. My name is Pam and I've been living with multiple sclerosis for almost 40 years. Just recently, I saw an article that talked about some research that uses the Optical Coherence Tomography machine to see whether or not a person might have multiple sclerosis. And I thought, well, that's a very interesting idea. So I will share with you the article, but I also will share with you the talk that was given recently at OHSU, Oregon Health and Science University, on a similar subject. So really the bottom line here is that we're now using tools that look at the eye to see what's going on inside our bodies in a way that I don't think we've ever done before. But first, I'll tell you about my experience with an OCT scanner. This was years and years ago, so that tells you this has been around for a long time. The eye doctor that I was seeing was the one that helped me with my optic neuritis issues, which is an interesting thing in and of itself. Didn't get any help from the neurologist, but my eye doctor was the one that helped me fix some of the vision problems I was having as a result of the optic neuritis. Anyway, after I don't know how many attacks of optic neuritis I had, but he was excited. He had just gotten this OCT machine. He wanted to look at my eyes so he could see how the scans compared with people who did not have multiple sclerosis. And lo and behold, we had no idea what we were really looking at, but we could clearly see there was something going on. There was some thinning. The colors were interesting. I didn't really understand it too well, but he was pretty happy with it. He just thought it was kind of neat. So it was more of just to satisfy his curiosity. We didn't do anything else with that. But looks like nowadays they're using OCT scans to do a lot more than they used to do when I had an OCT scan done. Here's a short video that explains how an OCT scan actually works.
Our ability to see relies on microscopic structures within the retina. X-rays, MRI, and ultrasound have been around for decades, but while the most sensitive of these, MRI, provides enough resolution to spot a brain tumor, it isn't sharp enough to visualize microscopic details. And so, a trio of scientists masterminded a pioneering technology, Optical Coherence Tomography. Capable of exquisitely sensitive real-time imaging, OCT has helped save millions of people from blindness. In the late 80s, MIT professor James Fujimoto and MD PhD student David Huang were building a device to measure corneal thickness using principles of light interaction. To measure using light, scientists split a light beam using mirrors, pointing one beam at an object and another beam along a known distance. When they meet back at the detector, the waves will be in different positions depending on how far they've traveled. From their combined height, scientists can calculate how far the object's surface is from the detector. The incredible sensitivity of their device meant they could see signals from inside tissue. With a prototype in hand, it was time to improve their system. They needed an engineer. Eric Swanson was working down the road at Lincoln Laboratories on intersatellite laser communication and high-speed fiber optic networks. He and Huang started adapting the satellite's receivers, fiber optics, and methods for steering light beams to build their OCT device. In the meantime, Huang realized that if they scanned the light beam, they could build a cross-section of the retina. They published this seminal work in 1991. Then, with the aim of getting it into the clinic, they shrank this mega OCT into one that was smaller and 100 times faster. By 1996, commercial OCT devices were in the hands of clinicians, and the microscopic capabilities soon became instrumental in aiding treatments, such as anti-VEGF therapy for age-related macular degeneration. This solidified OCT as a standard of care in ophthalmology. OCT continues to get faster and is pivotal in diagnosing and treating leading causes of blindness: age-related macular degeneration, diabetic retinopathy, and glaucoma. OCT is now the most commonly used ophthalmic imaging procedure, with a scan being performed somewhere in the world approximately every second. Thanks to Fujimoto, Huang, and Swanson, it looks like OCT's benefits have no end in sight.
I saw this article on July 24th of 2024 in Multiple Sclerosis News Today. It's called Machine Learning Analysis of Eye Scans May Aid Diagnosis of MS. Study finds algorithm detects slight changes that may be early MS signs. And the article goes on to say that using machine learning to analyze eye scans can help detect slight changes that may be early signs of multiple sclerosis, potentially aiding in early diagnosis of the disease, a study found. The study, SlowNet Enhancing Multiple Sclerosis Diagnosis Beyond Optical Coherence Tomography using Infrared Reflectance Scanning Laser Ophthalmoscopy Images, was published in Artificial Intelligence. MS is caused by inflammation in the brain and spinal cord. In most patients, the disease causes some amount of damage to cells in the eyes, and a building body of research is exploring whether eye-related changes may help diagnose MS. Infrared scanning laser ophthalmoscopy, or IRSLO, is an imaging technique that uses a laser to create a two-dimensional image of the retina, a region at the back of the eyeball that houses light-sensing cells. IRSLO is often performed in conjunction with another type of eye imaging called Optical Coherence Tomography, or OCT, which generates a two-dimensional picture of the retinal layers. But while OCT has previously been explored as a potential tool to help diagnose MS, IRSLO hasn't been thoroughly studied for this purpose. And they say that there are different models for diagnosis of MS. A team of scientists in Iran explored whether applying machine learning to IRSLO scans could help to identify MS. In machine learning, a computer is given a dataset alongside a set of mathematical rules or algorithms that the computer uses to identify patterns in the data. The computer can then use these learned patterns to make sense of new data, such as distinguishing between people with a given condition and those without. The scientists started with 265 IRSLO scans obtained from 32 people with MS and 70 people without the disease in Iran. A subset of these scans was used to train a variety of machine learning algorithms, and the remaining scans were used to test the algorithms. The best performing algorithm demonstrated more than 82% accuracy. It could accurately identify 83.1% of MS patients and 85.1% of those without the disease. Similar tests using only OCT images yielded slightly better accuracy. However, using both IRSLO and OCT scans in combination showed higher accuracy than either type of imaging on its own, reaching up to 96.9% accuracy. That's pretty good. This study is the first work in which machine learning methods were trained with two different imaging modalities for the diagnosis of MS, the researchers noted. The scientists further tested the machine learning tool on an external dataset of IRSLO and OCT scans from people in the U.S., and again the tool showed good accuracy, correctly identifying 97.3% of MS patients and 84.6% of those without MS. The study represents a significant step toward automated and precise detection of MS using a non-invasive, low-cost, and easily accessible technology, the scientists wrote, though they noted a need for additional studies with more patients to validate and further refine the tools. What really struck me when I was reading this, and maybe when you were listening to it, you saw this too, non-invasive would be wonderful. If we could get our MS diagnosed with eye tests rather than spinal taps, boy, wouldn't that be nice? And so to me, that's kind of the big thing right here. These machines, I don't know about the IRSLO, but the OCT machines are pretty widely available. So I know that they can't be that pricey. I know also, though, that they do require some skill in interpreting the results. So that might be an issue, but I think this is pretty promising. Here's a recent presentation from Dr. Elizabeth Silberman at OHSU talking about how they're using OCT to explore multiple sclerosis.
I'll be talking about visual outcomes in MS research today, and here's an outline of my talk. So I'll be talking about why we use the visual system as a model for MS, and I'm going to be reviewing a few different techniques that we can use to study the visual system. We'll start with structural measures. I'll spend the majority of my talk there. It's what I like to do. It's my area of research, and it's where we have a little bit more data. But I'll talk a little bit about functional measures as well, and then we'll talk about future directions. So visual dysfunction is nearly ubiquitous in people with MS. It's reported that upwards of 80% of people with MS have vision problems, and those vision problems can vary from people who have frank optic neuritis. So inflammation of the optic nerve can result in vision loss, color impairment. People can have difficulty with contrast vision, and they can have difficulty with problems with their eye movements as well. So given how common it is that people with MS have difficulty with their vision, you might be asking, is that because there's something different in the structure of my eyes? And the answer is yes. Within the scientific community, and as Lindsay beautifully alluded to, we oftentimes describe the retina as a window to the brain. And the reason for that is the retina, the lining of the back of the eye, is actually made from the same tissue that makes our brain and our spinal cord embryologically. And you can see some of the consequences of this shared homology here. Panel A shows a picture of a retinal ganglion cell, and this actually looks a lot like a primary neuron that you might see. You have a cell body, you have dendrites, you have an axon, and while the retina itself, this layer back here, does not contain myelin, retinal ganglion cells are myelinated behind the back of the eye to form the optic nerve, and that is what results in demyelination causing optic neuritis. Similarly, there's a lot of similarities in the structures called the inner blood retinal barrier and the systems that are within the brain. Becca Spain earlier had alluded to the fact that in progressive disease, there's thought that there is damage to the system that creates immune privilege within the brain, keeping bad things from the bloodstream from getting into the brain. The eye has something very similar, a series of both physical and immunologic properties that keep bad stuff from getting into the eye and out of the eye. And we can leverage this to learn about MS. So one of the really nice things about studying the eye is it's a lot easier to look in the eye than it is to look in the brain. And probably everyone here has had an MRI in the past. It is long, it is expensive, it can be very difficult to go through over and over again. So when we look at the eye, we have other techniques that have a lot of advantages that can give us really detailed information about the structure of the eye. And the technique that has the most kind of promise in this space is called OCT, or Optical Coherence Tomography. Now, OCT is very, very common. I would hazard that the majority of you, probably 75% of you, have had OCT done at your optometrist or your ophthalmologist office. You might not have even known. You put your chin in a machine, you look at a flashing light, and the test is done within about 30 seconds. But this is an example of what this machine is actually doing. In panel A, we're looking at a picture of the retina. So we're looking directly at the back of the eye. This is what we see when we look into your eye with a ophthalmoscope. And this technique, OCT, uses scanning light to take cross-sectional images of the retina and generates pictures down here. And what you might be able to appreciate is that there are all of these different layers that you can see within this picture. And these layers actually line up beautifully with this cartoon that you see here, which shows the actual anatomic cellular layers within the retina. So that scan that takes just a matter of seconds is giving us very, very highly detailed information about the structure of the retina. Now, like I said before, the retina is unmyelinated. So you might say, why do we care about an unmyelinated structure in MS? We know MS affects the myelin. But just like Dr. Spain talked about earlier, MS is a disease that also can cause neurodegeneration or death of brain cells. And when you look at the retina, you have these layers that are particularly interesting. There's this top layer up here. It's called the retinal nerve fiber layer. And this actually just contains axons. So it's very helpful to look for axonal loss. And then down here, the ganglion cell interplexiform layer, that contains the cell bodies. So you can pull out these layers, and within the retina, you can see kind of direct evidence of central nervous system damage. This is an example of what a readout looks like for an OCT. So if you were to ask your doctor to print you out one, it probably would look like this. You get this nice kind of color heat map. And then here, these areas of yellow show that you might have more thinning compared to age-matched controls. So that's an example of what an OCT looks like. And this became a really area of intense interest over the past 15 years, I'd say. There are probably thousands of papers on this topic, so I very briefly summarized it here. But the big takeaways is that OCT is able to measure thinning of the retina consistently in people with MS, with and without optic neuritis. And that thinning of that retinal nerve fiber layer of greater than 1.5 microns per year and the ganglion cell interplexiform layer correlates with disability progression. So over time, if that retina is thinning, that correlates with more MS disability. In addition, a significant thinning at a single time point actually also correlates with disability progression. And this was an area that was really powerful when people were designing clinical trials looking at medications that could perhaps remyelinate or lead to neuroprotection. This table is small, it's intentionally done that way. You're not supposed to read it, but these are just an example back in 2015, 2016, even at that time, of the number of phase 2 and phase 3 clinical trials that were using OCT as a primary outcome. And what people found is that thinning of the retina actually mirrors whole brain atrophy, whole brain shrinkage, with less variability than MRI. So within the research community, people became very excited about adding OCT in as a measure of brain shrinkage. As many of you probably know, when we develop MS medications, not only are we hoping for medications that stop inflammation, but the real gold standard or dream would be a medication that could slow brain shrinkage. One of the reasons that Dr. Spain's results earlier were so interesting. And we think OCT is a very reliable, inexpensive, and fast way of doing this. So OCT is well established in measuring brain shrinkage, and that's well established. But what I'll also share is that there are some other findings that may indicate that OCT can measure inflammation within the central nervous system. This is a paper that was published back in 2012 or 2013. And some researchers started to notice that some people with MS have these little black dots that you might be able to appreciate there where the arrow is. Also those black dots there in that area with that very small asterisk. And they called these microcysts. Very few people had them. They looked at 318 people with MS. They found only 5% of people had these microcysts. But people who had the microcysts were more likely to have optic neuritis. They had more severe multiple sclerosis. They had more trouble with their vision, and they had more retinal thinning. I left this map of the retina up here just to indicate, before we were talking about these kind of superficial layers, we're a little bit deeper in the retina now, the internuclear layer. So these microcysts were rare, but when people saw them, it tended to indicate more severe disease. And in a follow-up study, a research group found that if you have these microcysts, this layer of the retina actually becomes thicker. So everything we've talked about before is thinning. This is now getting thicker. And in people who had thicker internuclear layers, they tended to have more contrast-enhancing lesions and more lesions on their MRI scans. And this was exciting because previously we thought, well, OCT can measure brain shrinkage, but the reason we typically send patients to get MRIs is to look for new T2 lesions, new contrast-enhancing lesions. So this is the beginning of some evidence that perhaps there is something to be said for looking at OCT scans for other parts of the disease process. Now, I will say that there are questions about this, whether or not this is ready to take prime time, and by prime time, I mean into clinical practice. One, like I said before, it's very rare. Only 5% of people have it, so does everybody need to go sit through one of these tests in clinical practice? I'm not sure. The second is that you can see these microcysts in a lot of other disease states. Age-related macular degeneration, diabetic retinopathy, even healthy controls can have it. And we don't know what's causing those microcysts. All we see are these little bubbles. Some people say those little bubbles, those cysts, they're there because of inflammation. Other people say the layers of the retina are just physically pulling apart, causing these cysts. And one of the limitations in human research is it can be very hard for us to answer those questions. So I think it's an area that we should keep our eyes on in the next few years and see if anything evolves. For me, as somebody who does research in this space, I think it's pretty interesting and exciting. The second thing, and this is probably even earlier in its process, is there is some very early evidence that in OCT we might be able to directly see microglia. Again, we're looking at OCT scans here, and what these authors are seeing is there are these tiny, tiny white dots. Maybe easiest to see here. They don't project great, but maybe just trust where the blue and yellow arrows are. There are these tiny dots here. They're called hyperreflective foci. This study, they looked at healthy controls. They looked at 80 people with MS, and they found that people with MS had substantially more of these hyperreflective foci. There had been research done in another type of disease where they had seen these hyperreflective foci, and they were actually able, after that patient died, to do pathology of the eye and see activated microglia in those areas of the retina. And this led people to say, what if we can directly see immune cells? That's exciting because microglia are a big area in and of themselves within MS, but maybe we could look at whether or not there is activated inflammatory cells or immune cells in people with progressive disease. Maybe we could follow it over time. In this study, they found that people who had more evidence of inflammatory cells within the retina had more gray matter disease, so more MS lesions within the gray matter of the brain. And if you had fewer of these hyperreflective foci, you are more likely to have stable disease, what we call NEDA, or no evidence of disease activity, which is typically a combination of people being clinically stable, not having relapses, and not having new T2 lesions. So just to take a step back, I've gone through a lot of information about OCT. OCT is a good measure of neurodegeneration. It's fast, it's reliable, it's inexpensive. OCT may be a marker of inflammation that's based on these microcystic macular changes, and OCT may be able to directly show immune cells, and those are those hyperreflective foci. Okay. So moving from OCT, I'll transition to talk about OCT angiography. This is an area that I'm really interested in, an area where I've been doing research for the past 4 or 5 years now. OCT angiography is taking the technology of OCT, that same scanning light, but instead of focusing on the structure of the retina, we're now looking at the vasculature. And like I had said earlier, there are similarities between the structure of the blood vessels in the brain and in the eye. And this image should look similar to that cartoon I showed earlier. It's the same layers of the retina. But now you can see that there are these different blood vessel plexi or capillary beds feeding the different layers of the retina. So this technique gives pictures that look something like this, and you can image at different depths to be able to look at these blood vessels. And this was exciting for a few reasons. There has been a school of thought within the MS community for some time that damage to the blood vessels might drive the disease process of MS. And others think that the MS disease process causes secondary effects to the blood vessels. But we just didn't have a really great way of studying it. So this technique was really exciting. And I should say that a lot of the foundational work establishing OCTA was actually done at OHSU. You may recognize Becca Spain here. And she is sitting here with David Huang. And David is a very accomplished ophthalmic researcher who actually was one of the co-inventors of OCT early on in his training when he was at MIT, has been at OHSU for probably 10 to 15 years now and has continued to build the technique and was one of the kind of architects of OCT angiography. So we're really lucky to have his collaboration, and it's really exciting to bring his expertise into MS specifically. This paper was published back in 2018 and is looking at a slightly different technique, but they found that people with MS had decreased blood flow in the back of the eye compared to healthy controls. And in addition, people with MS with optic neuritis had even less blood flow than people without optic neuritis. And so this was one of the first studies that was published. The technique got better and better since then. And back a few years ago, enough work had been done that they could do what's called a meta-analysis, where people go through, they look at 30, 40, 50 papers and summarize the findings. And now what we see is it's pretty established. People with MS have fewer blood vessels in the back of the eye compared to healthy controls. People with optic neuritis have even fewer blood vessels than people without optic neuritis. In addition, people who have fewer blood vessels have more disability. And that's ultimately one of the important questions. Do these blood vessels mean anything? And the answer is they seem to at least correlate or go along with the clinical disability that you can see here. This is our EDSS, measures of walking speed, hand dexterity. So all of these are correlating with decreased blood vessels, and people who have fewer blood vessels don't see as well. So we think that that area is important, but as I alluded to earlier, one of the questions is what comes first, damage to the blood vessels or damage to the structure of the eye? And that was a question that I explored in a pilot study that isn't published yet. Hopefully will be published soon. The results are shown here. We enrolled 15 people with MS who were early in their disease process, within 5 years of diagnosis, and we scanned their eyes. And what you see here, the structural measures of the eye, the OCT, that's all up here. The blood vessel measures are down here. Our healthy controls are in red. People with MS without optic neuritis are in blue, and people with MS with optic neuritis are in green. And one of the things that was really interesting here is in people with MS without optic neuritis, they had fewer blood vessels, but actually the structure of their eye was normal.
Is that currently with optic neuritis or optic neuritis years past?
Great question. Optic neuritis years past, but in this study, we enrolled people within 5 years of diagnosis. I think the median disease duration was like 1.5 years. So everybody was relatively recent. And for some of those patients, optic neuritis was their first presenting symptom. Yeah, no, thanks for the question. And so this is exciting to us because it indicates that the blood vessels and the structure of the eye might be doing something a little bit different. We're not just looking at the sort of end marker of tissue dying away. There may be a sort of dynamic component of the vasculature that I think warrants more study in the future. So here's a summary of OCTA. OCTA measures vessel density in the central nervous system, and MS patients have decreased blood vessels in the retina compared to healthy controls, and this is even more so if you have optic neuritis. This may correlate with disability, and this may happen before retinal thinning, at least in early MS. I have a few ongoing studies, some of which people in this room were involved in, which is going to look at how the blood vessels in the eye change over 2 years. So we should have more data coming out soon. All right, I'm going to transition to the last part of my talk, which is focused on visual evoked potentials. So I've been talking about the structure of the eye, but the eye can also be used, or the visual system can be used to understand the function of the visual system as well. There's a technique called visual evoked potentials, and this technique measures cortical activity, so activity within the brain in response to what you're seeing. Some of you in the room may have had visual evoked potentials done. This technique was developed, I think in the 50s or 60s, before MRI. And so early on in the course of diagnosing people with MS, this used to be the gold standard before we could actually look directly at lesions within the brain. And there are two main outputs that we can see with visual evoked potentials. There's a measure that shows us the number of fibers in the pathway. So how many fibers are going all the way from the eye back and all the way into the brain. And then the latency, or the speed of conduction in the fibers. So how fast is the train moving? And this question of speed is really important with MS, which causes slowing. But it's very, very interesting to people who are developing remyelination therapies, because this is something that could improve if you improve myelin status. And this is just to show that 50% of people with MS can have optic nerve lesions here. But in addition, upwards of 70% of people with MS can actually have damage to other parts of the visual pathway, optic radiation lesions as well. So even if you don't have optic nerve dysfunction, you can still have abnormalities in your VEP. This is looks like a children's drawing of a VEP. It's a little bit simplistic, but the idea is that you have a person here, they're looking at a checkerboard, and they have these two electrodes on the brain, one here, one here. And in this form of VEP, the checkerboard will kind of alternate. Black will turn white, white will turn black, and then they're making these recordings. And I won't go into too much detail, but this is an example of what one of the recordings looks like. And if you have demyelination, like you would have in MS, everything shifts to the right, and that's what this right curve is indicating. And if you have remyelination, everything shifts to the left. So pretty cool technique. I'll give the caveat that for many hospitals around the country, probably around the world, people got a little bit rusty in doing VEPs. We didn't do them as much as we did before because we had MRIs, but some groups continue to do them. And an area that got a lot of attention is clemastine. Some of you may be familiar with the clemastine trial that came out a few years ago. Clemastine is an old medication that's a kind of an antihistamine. A group out of UCSF studied it as a remyelination agent. The design of the study is a little bit complicated. I won't go into it, but what they're looking at is that VEP latency. So how fast is information moving, and lower is better. And they found that actually in this study, everybody got clemastine. And by the end, you can see that everybody's VEPs got better. And they used this to say, we think that this medication might actually promote remyelination, in addition to other things. And this is another one of those kind of giant tables showing that in ongoing studies, looking at remyelination agents, a lot of them are using VEP still. Now, the next few talks will talk about kind of strategies for remyelination and may touch on some other measures. I am not advocating that VEP is the best, but when we talk about the visual system, it's something that's at least worth mentioning so that you know that that's one of the areas that might be of interest. So summaries on VEPs. VEPs directly measure myelin status. They show promise as a remyelination outcome. There are some limitations. There is variability between sites. You're only as good as the number of free throws you attempt, right? So if you don't do any VEPs and then you enroll in this trial, you may not be as good as a center doing hundreds of them, per month. And we still need to wait to see how it correlates with clinical outcomes. I'll close with just a few upcoming projects that I have going on right now. We talked earlier about OCT angiography and my work there. I'm working with the Imaging Research Center to look at whether or not we can correlate the changes that we're seeing in the back of the eye with blood flow measures in the brain. I think that'll be a pretty exciting study to really build that bridge between the retina and the brain. And I'm also hopefully about to start a project looking at ultra-high res OCT, which there are some example images here. This is that OCT scan that I was showing you earlier. There is a researcher at OHSU who was previously at MIT who developed a prototype of an ultra-high resolution OCT. And it actually has twice the resolution of this technique, and it's a proprietary machine. There's only kind of one just like this, maybe another one still at MIT, but all of a sudden the layers of the retina are really beautiful, really crisp, and we can actually pull out information that we couldn't see here. I think of it as like a Polaroid camera versus a digital camera. There is a lot that we can explore here, and as a kind of first pass, we have an upcoming clinical trial that Lindsay and I are doing together. We're calling it Breaking Out of the Box, and we're going to combine a few novel outcome measures for people with advanced MS. Lindsay's going to talk about it a little bit more in her talk as well, but here are just some brief details about it. We're looking for 20 people with any type of MS, and we're actually really interested in people who have some type of walking disability or walking impairment, but are still ambulatory. And that is because that group has historically been excluded from trials, and we really want to work to build information to develop more rational trials moving forward. I think we're going to have an opportunity to sign up for this out in the lobby afterwards, but there's also an email address here, and there are my citations. And here are all of the people who help me do what I do. A specific thanks to my mentor team, Becca Spain, Dennis Bordet, and David Huang, the whole MS Center. And thank you all for your attention.
So the eye really is a window into our brains, essentially. Apparently, it's made of the same tissue, or at least the back of the eye is. And the optic nerve, though you rarely hear it listed, is actually part of the central nervous system, which makes it different from our other senses. They are part of our nervous system, obviously, but not in the intimate way that our eyes are. So looking into our eyes to see the state of our health is quite an interesting and logical thing to be doing, I would think. They did mention that there was a clinical trial that they were in the midst of recruiting for it. I think I would be a good candidate for it since I have had many bouts of optic neuritis, even though it hasn't happened in years. Maybe my optic neuritis is too old? I don't know. But when the eye doctors look in the back of my eye, they say, yeah, you've still got quite a bit of pallor back there. So there's been some structural damage in the vascular system of my eyes. And that's what they look for when they determine whether or not we are undergoing damage from multiple sclerosis. And hey, look at this. I had volunteered for that clinical trial, and lo and behold, I just got a message back from them, and they sent me the consent form, and it looks like I'm going to be part of that. So I will be able to let you know how that turns out. I'm pretty excited. That's all I have for you today. So until my next video, do take really good care of yourself and let me know in the comments if this research is something that you're excited about.